Today we're on page 1 of the Chapter 8 and 9 AP packet on bonding, and we're going to be looking at two different kinds of bonding, ionic and covalent. We're going to start with ionic, and as you recall, ionic is an attraction between two oppositely charged ions due to a transfer of electrons from the metal to the non-metal. So ionic bonding is always going to be a metal and a non-metal. In this case, we're going to look at Na plus and Cl minus, sodium and chloride. So as you can see from this diagram, the sodium is the positive ion and the chloride is the negative ion. You could actually figure out yourself that the Na is the smaller one because Na plus is going to end in a 2p6 versus Cl minus is going to end in a 3p6. And so you know because of shielding and higher energy level, chloride is going to be larger than the sodium ion. So let's figure out the force of attraction between the two ions, Na plus and Cl minus. We're going to use Coulomb's law to do that, where E is the energy of the attraction. There's a constant. Q1 and Q2 represent the charges. So the Q2 is whatever the negative is, the Q1 is whatever the positive is, and R is the radius between the two ions. So if we're going to plug this in to our equation, we'll write E equals negative 2.31 times 10 to the minus 19th, and that's going to be in joules times nanometers. And then we're going to need to know the two charges. So the sodium is just a +1, and the chloride is a -1. And then you're going to divide by the radius that was given in the problem, which is 0.276 nanometers. You're going to need to use nanometers for this because you want nanometers to cancel out on the numerator and denominator. And when you're all done, you're going to find out that the answer is negative 8.37 times 10 to the minus 19th joules. Now that's only for one set of Na plus and Cl minus, all right? But if you want to get it for a mole, then you have to multiply it by Avogadro's number. So if you do that, you're going to get the lattice energy equal to negative 504 kilojoules per mole. And that would be the lattice for sodium chloride, lattice energy. Now this is how to get a specific number, but let's suppose you just had to compare the two. Compare two lattice energies of different ionic compounds. Well, if you look at the formula, you could see that if you want to have a high lattice, meaning releasing lots of energy, you'd want to have either big numerator or small denominator. So what would happen is if you had something that had a +2 and a -1, such as magnesium chloride, that would give you double this amount up top. And of course the nanometers would be different, but not significantly enough as much as the charges. So always look at charge first and then look at size second. Always look at charge first, then size second. So if we had to compare these 5 different salts and their ionization energies, their lattice energies, we're going to first look at their charges. So this is a +1, -1, +1, -1, +2, -1, +2, -1, +3, -3. So all of a sudden you know that aluminum phosphate has to be the most lattice because it has the highest charges. Okay, so we're done with this one. Now we need to figure out these two are going to go in these two blanks, and these two are going to go in these two blanks, and we have to look at size. So chloride and bromide, if you look at the periodic table, chloride ends in a 3p6, bromide ends in a 4p6. So they want the smaller size. Smaller size gives you more lattice. So that means that MgCl2 will go there, and MgBr2 will go here. And now we're going to look at these two. We want the smaller size. The smaller size is lithium and fluoride. Both are smaller than sodium and chloride. So this would be here, and then this would be the least. Now we're not going to give you a question that would be like, let's say, Na with F and Li with Cl, because the smaller size is the lithium and the smaller size is the fluoride. So we're not going to give you a situation where the small one over here, there's a small big here and a small big here. We're not going to do that. It's going to be 2 smalls versus 2 bigs, etc. So this would be the order for the lattice energy of these 5 salts, and that was just very qualitative without having to do all this big calculation. And lastly, all bonds fall within the range of ionic versus nonpolar. Okay, so there's ionic as a metal and a nonmetal. A completely nonpolar would be any of the diatomic elements. And then everything in between is going to be some sort of polar, in this case a polar covalent, because they're sharing, because they're 2 nonmetals, but they are not equal sharing. The chloride has a stronger electronegativity than the hydrogen, and so we learned how to write that. You would write something along the lines of HCl, and then you'd either point towards the Cl like this, or we learned that what you could do is write HCl and then put a delta negative, delta positive to show the polarity of the bond as well.